In this video, we're going to go through some solutions to select equilibrium problems, specifically Chapter 15, 49 through 59, odds. Here's problem 49a. We're given this equation with this equilibrium constant. We're also given the mass of Br2 at equilibrium and the volume of the container. Now it's important to note that the volume of the container will be equal to the volume of any gas that's in the container, because every gas, whether it's in a mixture or by itself, will occupy the entire container and take up the volume of the container. What we are charged to do here is solve for the mass of Br at equilibrium. So we know the mass of this chemical at equilibrium. We want to find the mass of this chemical at equilibrium. Now, equilibrium calculations have either pressure or concentration. We can't calculate equilibrium calculations with mass. So the first thing we're going to do is turn this known mass for Br2 into a concentration. So set it up so that grams crosses out and becomes moles using the molar mass of Br2 that we add up off the periodic table. Then we take the moles of Br2 that we have from this and divide by the 0.2 liters that was given in the problem. And that will give us the concentration as 7.67 times 10 to the negative third moles per liter, or molarity, of Br2. That's our equilibrium concentration of Br2. Here's the equilibrium expression. We know that we can solve that for the concentration of Br. So we're going to take the concentration of Br2 and multiply it on both sides so it moves up here. Then take a square root of both sides, and that would give us the equilibrium concentration of Br. I'm going to label that EQ. Now remember that when you're calculating a Kc value, these are equilibrium concentrations. I'm just labeling that EQ here for Br concentration. Plug in the numbers that we know. This is our Kc value, right? And this is our calculated concentration of Br2. Solve, and we get 2.82 times 10 to the negative third molar concentration for Br at equilibrium. Now remember that this is a unitless constant, so we have to make sure we put that unit of molarity in there. Now we want to calculate the mass of Br. So to calculate the mass of Br, what we're going to do is take that molarity that we just calculated here, and let's label it moles per liter now. Here I have it labeled with capital M, but that's moles per liter. Multiply by the volume of the container, 0.2 liters, and then liters will cross cancel. And then we'll have moles. And to turn moles into grams, we just use the molar mass, set it up so that moles cross cancels, and we'll get 4.5 times 10 to, 4.51 times 10 to the negative 2 grams as our answer for the mass of Br at equilibrium. Here's problem number 49b. We're given this equation with this equilibrium constant. We're also given the volume of the container, the mass of the H2 at equilibrium, the mass of the I2 at equilibrium, and what we want to calculate is the mass of HI at equilibrium. So once again, the first thing we have to do is take these mass values and turn them into concentrations. So here's the mass that was given for H2. Using the molar mass of H2 from the periodic table, set it up so grams cross cancels and we'll get moles. Then divide by 2 liters. So I'm just going to do that as an inverse of 2 liters multiplied. So we'll get moles per liter here, or 0.0139 molarity of H2. That's moles per liter. We do the same thing for I2 using the mass of I2 and the molar mass of I2 that we add up off the periodic table. Divide by 2 liters again, and that gives us the molarity for I2 as 0.00859 molar concentration of I2. Now these are the concentrations at equilibrium. So here's the equilibrium expression, and we know that from what the balanced equation tells us. We can put that together. Plug in the numbers that we know for Kc that was given in the problem, and for the concentration of H2 and I2 that we just calculated from here. Solve for the concentration of HI, Now, since that's a squared value, there's going to be a square root involved with that. And that turns out to be 0.0813 molar concentration of HI. We need to find the mass. So what we're going to do is take that molar concentration, and again, instead of expressing it as just capital M, I'll express it as moles per liter now. Multiply by liters. That's 2 liters that was given in the problem. That's the volume of any gas in the container. Then use the molar mass of HI that we add up off the periodic table such that moles cross cancels and then grams carries in the answer. You should get 20.8 grams for the equilibrium mass of HI. Here's problem number 51. In problem number 51, we're given this balanced equation with this Kc value. We're given the initial concentration of NO, the initial concentration, or rather the equilibrium concentration of NO, N2, and O2 are what we're supposed to calculate. So we're going to set up this rice table, or you could call it an ice table if you want. Here's the reaction, the balanced equation. Here are the initial amounts, and we're starting out with 0.175 molar concentration of I, and of NO, and we are starting out with 0 molarity of N2 and 0 molarity of I2. Now, the stoichiometric relationship 2 to 1 to 1 of the chemicals is what tells us how the change is going to go. So we have 2x to 1x to 1x for the change as we progress towards equilibrium. Since we have some of this chemical to start with, that's going to diminish, so it's going to be minus 2x. And since we're starting out with 0 amounts of these chemicals, and we know that if initially we have this chemical and we don't have any other initial amounts given, they must be 0. So then if we're starting with 0, as we let the reaction go, those amounts will increase. These are going to be positive amounts of X that we have there. So combine the initial line and the change line to get the equilibrium line. So 0.175 minus 2x would be the equilibrium amount for NO. 0 plus x, or just x, is the equilibrium amount for N2, and x is the equilibrium amount for O2 as well. So here's our equilibrium constant expression that we can put together, knowing what the equation is and what these coefficients are. Remember, we always have the product of the concentration of the product chemicals raised to the power of their coefficients, and they're both 1, divided by the product of the concentration of all the reactant chemicals. Well, there is only one reactant chemical, raised to the power of the coefficient. Let's plug in the numbers for Kc, and then we know that the equilibrium concentration of N2 and O2 are both X, right? That's X and that's X. And this is the equilibrium concentration of NO. This is right from the rice table. And remember that we have to square that value. And you know what? It's very important that you are meticulous with your calculations rather, when you do the equilibrium problems. Now, you could just jump in and solve this with the quadratic equation. That's the long way to do it, but you could do it this way, where you take this, multiply it by that side of the equation, and x times x is x squared. That's the other side. Multiply that stuff out using the FOIL method, I guess, and you could end up with this equation. We're going to distribute this value into this side of the equation and get these numbers. Still have x squared on the right. And then let's get 0 on the right-hand side by moving that x squared over to that side. Use the quadratic equation, and you solve that so that x is either 0.090 or 0.087. Now, if we plug 0.090 into here, that's what I've done here, you end up with a negative value. Well, we can't have a negative concentration for any chemical. So that means that 0.090 is too big. It can't, oops, sorry about that. 0.090 is too big. It can't be a solution. So 0.087 has to be the solution that we're looking for. Now, that's the long way to do it. That's a lot of calculating. Here's a shortcut solution, and you should always look to try to avoid using the quadratic equation if at all possible. And this happens a fairly good amount of time, where notice that x times x is x squared, and this value down here is already squared. So the right-hand side of the equation is a square over a square. Well, we can just take a square root of that to simplify that out. So if we take a square root of both sides of the equation, take a square root of this side and that side, square root of this is 48.99, and the square root of x squared is x, and the square root of 0.175 minus 2x quantity squared is 0.175 minus 2x. Now we can do a little algebra. Take this quantity and multiply it by that, and that'll be equal to x. So this times this is this number. No, I'm sorry, I guess that's not true. Kind of added it together and manipulated it in this line right here. So if we combine all the x's, we get 98.98x is equal to 8.573. If you solve for x there, you get that x is equal to 0.0866. Hey, that's the 0.087 we had there, right? So we know the equilibrium concentration for N2, which is x, is equal to 0.087. And for O2, it's 0.087. And for NO, now notice that we have 3 decimal places here. So I think it's a good idea that we don't just say 0.087. Let's say 0.0866. And when you do that, you end up with 0.0018 molarity, which rounds to 0.002. If you use 0.087 here, you won't get that level of precision. And with such a small number, we really do want to be more precise. So I think it's worth using these extra decimals here. So when in doubt, keep those extra decimals and keep them in the calculation. And I guess you could use them here too if you wanted to. So try not to use the quadratic if you can avoid it. Save you a lot of grief. Here's number 53. We have this equation, right? This equation with all those. And Kp is 0.416. We always have the temperature specified for these problems because Kp is temperature dependent. The equilibrium state is temperature dependent. We know that we're given in the problem that the partial pressure of NOBr at equilibrium is the same as the partial pressure of NO at equilibrium. Now that seems like, okay, well, what are we going to do with that? Well, we can actually calculate the partial pressure of Br2 here at equilibrium. Here's the equilibrium expression for pressure. So the partial pressure of this chemical squared, because there's a 2 coefficient, multiplied by the partial pressure of this chemical to the first power. We don't write that first power in there, but that's because there's a 1 coefficient here, which is also unwritten 1. And we divide by the partial pressure of the reactant squared. Because of that 2 coefficient here, we have a square. Now, I could substitute in x squared and x squared since these are the same. And whatever they are, they're going to cancel out. They're the same. So we get that the partial pressure of Br2 is just equal to 0.416. Right? This is the only thing left on the right-hand side of the equation once we cancel out those 2 values. And that would really be true for any partial pressures that we start with if they are equal at equilibrium. So that's kind of a nice thing to pay attention to. Now for number 55, we're given really a solution process where we take the solid and it goes into solution as these positive ions and these negative ions. And notice everything's a 1-to-1-to-1 ratio. That's because there's 1 Ca and 1 SO4 that makes up this compound. So when it breaks apart into ions, there's 1 Ca and 1 SO4 that are in solution. Here's the Kc for the process. Can't really call it a reaction, I guess, because we're just making a solution here. So if excess calcium sulfate solid is mixed in with water to make a saturated solution, what is the equilibrium concentration of calcium ions and sulfate ions? Oops, this should say EQ. What is the equilibrium concentration of those chemicals? Well, notice that when we write the equilibrium expression, we have to omit pure solids and pure liquids. So this is not in the equilibrium expression. This is it. Now, since this is a 1-to-1 ratio at equilibrium, these 2 numbers must be equal to each other. So let's just call them x. So we can say that the equilibrium constant, Kc, is equal to x squared. It's equal to this if we call it x times this if we call it x, or x squared. So we solve for x and we get 0.0049. So we can say that the concentration of the calcium ions at equilibrium as well as the sulfate ions equilibrium, because they are in a 1-to-1 ratio, is 0.0049 molarity, or molar concentration. Now, if we know the volume in this reaction is 1.41 liters, what is the minimum mass of calcium sulfate solid, it's the minimum mass of this, that we need to add to water to make it a saturated solution with a total volume of solution of 1.4 liters? Well, we know from this previous calculation that at equilibrium in a saturated solution, we have Ca2 plus equal to SO4 2 minus equal to 0.0049 molarity. We just solved for that. That's the concentration of the saturated solution. And that really comes from our parameters that we set here in this beginning of the beginning of the problem here in part A. So we know that from the balanced equation, since there's a 1-to-1-to-1 mole ratio, that the amount of Ca2 plus and the amount of SO4 2 minus must be the same as the amount of CaSO4. So to make a saturated solution, we would need 0.0049 moles per liter of CaSO4. Since we have 1.4 liters, we can multiply by that, so liters cancels out. And now we would have moles of CaSO4, so let's turn that into grams using the molar mass of CaSO4. So this 131.16 is adding up the molar mass of Ca and S and 4 O's. So we set it up so moles cross cancels and grams carries into the answer. So that's how much CaSO4 you would have to dissolve. The minimum amount that you would have to dissolve to get a saturated solution. It's 0.934 grams. Here's problem number 57. In this problem, it says that we have this equation and this equilibrium constant. We know the initial number of moles of this chemical is 0.5, and that we have a 2-liter flask that's allowed to go to equilibrium. What we want to do is calculate the equilibrium concentration of I2, the equilibrium concentration of Br2, and the equilibrium concentration of IBr. So we set up our Rice table, or if you already have the reaction here and don't want to rewrite it, you can just write the ICE table. We know that initially we're starting with no concentration of this or this. So we're starting with concentration of that product. Now, if there's none of this to start with, as the reaction progresses, we're going to actually start adding that in. So we have to be careful that because this is a 1-to-1-to-2 ratio, we say it's x to x to 2x in our change line. The change line always reflects the ratio of the coefficients. And we have to be careful now because at equilibrium, we can't have a negative concentration, right? So 0 plus x would give us x at equilibrium. Same thing over here. And some of this would diminish as it goes to equilibrium. So 0.25 minus 2x would be the equilibrium amount for IBr. Remember, this is a reversible reaction. So essentially, this is kind of the reactant here, and these are kind of the products because of the way we have this set up, where we're starting with this chemical and we have none of that chemical, of either of those chemicals. So just be careful about your plus and minus signs. Remember that you can never have a concentration that's negative. So we can't have a negative initial concentration. We can't have a negative equilibrium concentration. All right, so then here's our equilibrium expression. Plug in the values that we have for these equilibrium amounts. So for IBr concentration, it's equal to this quantity, and since we square it here, we have to square it here. Right, this is where that comes from. The concentration of I2, well, that's just x at equilibrium. And the concentration of Br2, well, that's just x at equilibrium. So now we can rearrange this. Actually, I guess the first thing we're going to do is simplify it. We have a squared value here, and x times x is x squared. So we have a squared value over a squared value. To get rid of that square, we can just do a square root of both sides. So we plug in 280 for the Kc value, do a square root of both sides, that'll get rid of these two squares. And we get that square root of 280 is 16.73. On the right hand side we have 0.25 minus 2x divided by x. So you would just do the algebra there and solve for x, and you would get 0.0133. So our equilibrium concentrations that we're looking for, I2 is just x, so it's 0.0133. Same thing for BR2, 0.0133. And for IBR, well, that's equal to 25 minus 2x. So if we plug this number into here, we end up with 0.223 as our equilibrium concentration of IBR. Now for this last problem, you do have to use the quadratic. There's no way to simplify it. We're given this equation, we're given this Kp value. We know the initial concentration of CH4 is 105.1, or rather the initial partial pressure. The initial partial pressure of I2 is 7.96, and those are measured in torr. Since we don't have any initial partial pressure of any other chemicals, we assume that there's zero amounts of these chemicals. And what we want to do is calculate the partial pressure at equilibrium for all these chemicals. So let's do our Rice table. Here's our reaction. Plug in our initial starting amounts, so 1.05, 7.93, and then 0 and 0. From the stoichiometric relationship, we know that we're going to have negative x, positive x, and positive x because we have a 1-to-1-to-1 ratio. Since we're starting with none of these chemicals, we're going to add to that as the reaction progresses. And since we're starting with some of these chemicals, they're going to diminish, so they're going to be negative amounts of x as the change occurs. So at equilibrium, 105.1 minus x would be the equilibrium amount of CH4. For I2 at equilibrium, the equilibrium amount, or the equilibrium pressure, would be 7.96 minus x. And then for these two, 0 plus x would give us x at equilibrium for both. So we know this is our equilibrium expression, equilibrium constant expression. Plug in the Kp value that we know. Plug in x here for this chemical, and x here for this chemical for pressure. Plug in this for the pressure of CH4 and this for the pressure of I2. Rearrange this denominator, or I guess combine this denominator so it looks like this. And then x plus x is x squared in the numerator. Now we're going to rearrange it so that we have this quantity multiplied by that value here on the left of the equality sign or equal sign, and x squared to the right. Manipulate that so that we have all of the values on one side equal to 0 on the other side, and now we can plug into the quadratic equation. Negative b plus or minus b squared minus 4ac divided by 2a, where this is a, this is b, and this is c. So a negative of that number plus or minus this number squared minus 4 times that number, that's a, multiplied by this number, that's c. So again, b squared minus, or rather negative b plus or minus the square root of b squared minus 4ac. We're going to divide that by 2 times this a value, so divided by 2a. When you solve for that, you get 4.22, or you get negative 0.448. Now that negative value is always going to be meaningless for concentration, so we can just ignore that. So we know that x is 0.442. All right, so then since the concentration of this chemical at equilibrium is x, we can just label that. And we're talking about pressure in torr, so we're going to call these torr pressures. We know the pressure of that is x at equilibrium. We can solve for that. We know the pressure of CH4 is 105.1 minus x, so 105.1 minus 0.442, it's 104.7. And the pressure at equilibrium for I2 is 7.96 minus x, or 7.96 minus 0.442, which is 7.54 torr. Good luck.